Okay, thank you so much to the conveners for the invitation for this session, and also to Kristen for setting up my talk very nicely. So I'll be talking a little bit more about the flip side of the global carbon cycle and potentially the burial of organic carbon from the ocean. And I should mention my co-authors on this work, Dalton Hardisty, Benjamin Gill, and Tim Lyons. But really, I'll be showing a synthesis and summary of a lot of published data by the community. So this really represents really a community effort in thinking about how we can track redox conditions in past oceans and how we can evaluate them for potential issues from diagenesis. Okay, so tying back to this theme of sustainability, ocean anoxia hypoxia is a growing concern, namely because these low oxygen environments can really affect fisheries and coastal resources for communities that rely on them for their economy and for food sources. So this is a distribution of oxygen in modern oceans, and you can see that there's a huge range of redox conditions from the white areas, which represent high oxygen conditions, to really low reducing areas such as the Black Sea, which is the type example, which is so reducing that there's free hydrogen sulfide in the water column. But there's a whole suite of other areas which are called hypoxic, where there's some oxygen, but it's very low. So key examples are the Gulf of Mexico, as well as upwelling zones, such as the coastal of Namibia. And so in my talk, I'll be referring to many of these conditions as anoxia, simply because as geochemists looking at the rock record, it can be hard to distinguish between these different gradations and degrees of deoxygenation. And so the connection between anoxia and habitability is also shown very nicely by the correspondence between mass extinctions and the deoxygenation of these marine environments. So this figure is showing anoxic events as inferred from the deposition of black shales from the Paleozoic until today. And these arrows mark the presence of mass extinctions. Now this figure is a bit old now, it's 20 years, and so it could be updated. And namely, many anoxic events have now been identified that match up with these arrows. And of course, periods of marine anoxia also coincide with the enhanced deposition and preservation of organic carbon. So this is an older figure again, but I think it does a really nice job highlighting these intervals of oil and gas source deposition periods, and they often correspond to periods of high rates of black shale deposition under the assumption that oil and gas comes from rocks with high organic carbon content. And so all these questions drive the need to understand why it is that anoxic events happen in Earth history, what drives oxygenation and deoxygenation of the oceans, in order to understand the future sustainability of the oceans, as well as some of the more economic resources that are important for our economy. It's really difficult to know what oxygen concentrations in the oceans were like. We can't go back and measure them, and so we have to rely on proxies. And so proxies have already done a huge amount of work in advancing understanding of how redox conditions have changed through the past. So this is a cartoon showing the inferred evolution of atmospheric oxygen through time. And you can see that there's quite a bit of topography that has come about from using inorganic proxies for redox conditions. And I'm focusing on inorganic proxies primarily because they can represent redox conditions at a broad range of spatial scales and at different sensitivities. And they can be analyzed in multiple sedimentary archives, so they can be compared. Thanks to technological advances, there's a whole suite of, whole toolkit of proxies that have now come to the forefront, and they vary in many different ways. So for example, you can classify them as global proxies or ones that can integrate over a really large global ocean scale. There's also local proxies, which can tell you about a basin perhaps, or for your sample itself, what the oxygen was like for that specific depositional environment. But you can also group them in how they can be analyzed. So you can see from this distribution that much of the work of developing these proxies has focused on shales. But in my talk, I'm going to really focus on the ones in carbonates, and namely iodine-calcium ratios, serum anomaly, which is cerium normalized to a shale value and also relative to its neighboring rare earths, sulfur isotopes in carbonate-associated sulfate, which is denoted as delta 34S, and uranium isotopes, which I've denoted here in delta notation as delta 238 uranium. So I've also selected these because there is an emerging effort to produce long-term, deep time records of these proxies to track the long-term evolution of the oceans. In addition, these have been the focus of a lot of work of diagenesis in the past few years, and so I'm going to highlight these for the rest of my talk. As Kristen just discussed, carbonate records present really unique advantages. So she showed a nice complement to this. So this is a proportion of carbonate columns from North America, and carbonates are in blue. And the main takeaway is just that carbonates have been, you can find carbonates ranging from the early Proterozoic until today. So they're very spatially and temporally well distributed. And they also tend to have higher sedimentation rates than shales. And so you can also sample events at higher temporal resolution. Of course, it's really important to admit that they also have significant challenges, and that's namely potential alteration from diagenetic processes. And so I'm showing you two different scales in which you can see this. On the left is a slab of a Middle Triassic microbial reef boundstone, and you can just see all the cements that have precipitated since deposition. And of course, you can also get alteration on really large landscape scales, with the classic example being the Dolomite Mountains in Italy. And so it's pretty clear, as Kristen mentioned, that all of these rocks have seen significant syn and post-depositional alteration. And so the question is, does this mean we have to throw it all away, or what information can we still extract from these records? Of course, our understanding of the evolution of oxygen in the Earth oceans really relies on carbonate chemistry. And so it's an imperfect tool, excuse me, but it is what we have. And so it's important to not turn away from this record and really just think about how can we assess and account for diagenesis to alter our interpretations of these geochemical records. Okay, so I'm going to go through those 4 proxies I discussed, and I'll show you that data that's been compiled, again, by many, many authors, many, many researchers in the field. I'm just plotting them all against each other for my talk. And so I'll show you the data from 3.5 billion years ago until today. So first, sulfur isotopes. I'm not going to get into the systematics. I'm happy to explain that to you afterward, but you can just take my word that we'll interpret it from the redox lens in this way. And the main first order trend I want you to notice is that there appears to be a decrease in variability after about 400 million years ago. So a lot of noise, and then it seems to quiet down a bit. Now, sulfur has many ways you can interpret it, but one of them could be an increase in the sulfate reservoir of seawater. And so that would require an increase in oxygen as well in the oceans. So next, here's the serum anomaly data. Again, the first order trend is values that hover around 1 until about approximately 400 million years ago, at which they start to decrease. If we were to interpret this using a redox lens, we would say that there was an increase in more oxic oceans after about 400 million years. Now, this is not to say that prior to 400 million years ago, the entire ocean was anoxic. That's not what I'm saying at all. It's just that there seems to be an overall shift to these more well-oxygenated conditions. And in fact, there certainly was a lot of spatial heterogeneity throughout this period. Next, iodine-calcium ratios. Again, the first order trend is an increase in ratios. They always have low values, but if you look at the maximum values, they tend to go from low values to higher. And it's a little bit harder to tell, but perhaps it's around 400 million years ago. Again, you would interpret this as an increase in oxic conditions. And finally, for uranium isotopes, there's fewer data here, it's important to note, but there's the general first order trend is increasing values from the Cryogenian until today. You would again interpret this as a shift to oxic conditions. Okay, now obviously there's a ton of caveats that need to be, that I need to say, namely being that these sample different lithologies, different facies, and so it's really hard to control for that. They sample different rock size, sample sizes as well, but nonetheless they seem to show this first order trend. They also represent different sensitivities of redox conditions, and so it's not always easy to interpret them simultaneously. And lastly, and this is obvious to everyone, but they've been sampled at different resolutions. And this is particularly obvious for uranium isotopes, which really has focused on perturbations. And so really being able to compare baseline conditions can sometimes be tricky. But nonetheless, I think combined, the most parsimonious explanation could be that there was an increase in oxygen at about 400 million years ago. And the nice thing is that this matches other lines of evidence, including from models, as well as the overall hypothesis that the Paleozoic saw an increase in oxygen both in the atmosphere and in the oceans with the advent of land plants, which led to increased organic carbon burial on land and the rise of oxygen. But of course, there's significant variability. And so in addition to my potential interpretation that this represents changes in redox conditions, we also have to ask, well, could this just represent a change in the diagenetic regime as well? So in other words, a real question is, can we identify the seawater signal through the diagenetic noise? This is not a new question. People have been thinking about this for a long time, namely for carbon and oxygen isotopes. And so I want to lean on some of that data and show that this has now been, these same tools have been utilized for these Paleoredox proxies as well. So some of the classic studies looking at the effects of diagenesis on geochemical records and carbonates comes from a whole suite of studies from Kleino and Unda and other cores that were drilled in the Great Bahama Bank. And so if you looked at this data, this is delta 13C, without any context, you might say, oh, look, there are some large negative excursions. Of course, the Pliocene ocean didn't experience carbon isotope perturbations to this degree, and instead this represents meteoric diagenesis from sea level changes due to the last glaciation. And so this should give us pause about interpreting these records very simply as changes in seawater. And again, the community has taken a similar approach in looking at these Paleoredox proxies. So I've just compiled some of these data here. So this is data also from Kleino and Unda, iodine-calcium ratios here, the cerium anomaly, sulfur isotopes, uranium isotopes. Again, these are a little bit less well studied, but I think the main takeaway, which you can still see from this, is that the range of data in these recently altered carbonates nearly matches the range of proxies observed throughout Earth history. So again, this would give us pause and make us want to be sure that we're interpreting our data very carefully. And I think with these new data sets, there's a ways in which we can do this evaluation. And this would require combining statistical analyses with new modeling approaches, well, really taking advantage of well-established modeling approaches and combining them to really look at the data more carefully. So first, let's look at some statistics. Thanks to all this data that's now been collected as a community effort, we can plot the distribution of iodine calcium, for example, which is what I'll use here, in different bins. So here's all the modern data. Here's the data from Kleino and Unda, so the meteorically altered carbonates. This is the Mesozoic and Cenozoic all bin together, the Paleozoic, and the Precambrian. And what should be immediately obvious is that the distribution of data from the modern don't match any of the other distributions. And this is really obvious when you look at Kleino and Unda, which again are not anticipated to have experienced significant changes in redox conditions to the degree that we would have expected deeper in Earth history. So specifically, the distribution itself and the values don't really seem to have much overlap. So just some simple statistics to highlight this. I've shown the mean of these different time intervals that have been binned here for each of these proxies. If we just look at the modern versus Kleino and Unda sites, again, we don't expect that there should be large redox changes here, so they should ideally match very nicely. That's not the case at all. They're quite different. And so it does not seem that Kleino and Unda can represent seawater very well. We can also look at the symmetry of the distribution, or the skewness, where 0 represents a normal distribution. More positive values are right skewed and negative values are left skewed. Again, we see that they're dramatically different. And so the other question we have to ask, however, is whether or not Kleino and Unda are representative of diagenetic environments in general. Okay, so what we want to do is pair some of our observations from the simple distribution of the data to make predictions about why they might change using modeling approaches. And I'm going to be showing you some data from water-rock interaction models, similar to this classic example that was presented by Banner and Hansen. This is showing the evolution of strontium radiogenic isotopes and strontium concentrations with increasing N, where N is the water-to-rock mass ratio. And I'm choosing strontium here because strontium has long been noted to vary depending on the original calcium carbonate polymorph, whether it's aragonite or calcite, in addition to showing a lot of loss during recrystallization. So here's a similar model result. Again, the main goal of this is to track geochemical change of a carbonate rock as it progresses to equilibrium with some diagenetic fluid. So this example, I'm showing how a shallow marine carbonate, the delta 13C and delta 18O, would change as it interacts with increasing amounts of seawater. The blue is an open system, meaning it's more fluid buffered, and closed system means it's more sediment buffered. And what becomes immediately obvious is that the initial value, which is this gray dashed line, the propensity to shift really varies depending on the different chemical constituents. Again, this isn't new. People have long known that oxygen isotopes are really readily reset, whereas carbon isotopes tend to be more robust. But we want to take this pretty simple approach just to compare our different redox proxies. So this is the same situation, a shallow marine carbonate interacting with seawater. Here's the carbon isotopes, oxygen isotopes, strontium concentrations, sulfur isotopes, iodine-calcium ratios, serum anomaly, uranium concentrations, and uranium isotopes depending on whether or not you're precipitating aragonite or calcite. So some of the things we want you to note is that there's no predicted change in iodine, calcium, or serum anomaly. In contrast, the sulfur isotopes tend to shift pretty readily at relatively low water-rock ratios, whereas the uranium isotopes represent intermediate mode, meaning they do become reset, but it takes a bit more fluid flow in order to make this happen. And so this is able, so with this framework, we can compare the propensity for the susceptibility of each proxy to be altered with different fluids. So here's a similar result showing what we might predict with meteoric diagenesis to the left, and then diagenesis with the reduced brine to the right. There's a ton going on here, so I just want to point out some of the key features, namely that we can also make predictions about how these might shift. So if you look at iodine calcium, for example, we see that under diagenesis with meteoric waters, you would see a pretty large shift. And again, this matches the data from Kleinow and Unda very well, which you see that the mean value and the distribution definitely skews toward lower values. So we can start making these mechanistic predictions of how they might vary. So in order to make a better comparison, I'm going to take a snapshot of each of these model results. So I'm looking at the data at a water-rock mass ratio of 500. So for example, at that point, 100% of oxygen isotopes are reset, whereas for carbon, it's about 10%. So we can plot all of our geochemical proxies of interest here, where again, 0% is no resetting, 100% is all resetting. Let's first look at the seawater situation. I've boxed in yellow the Paleoredox Proxies of interest. Again, as we said earlier, sulfur isotopes, they're more easily reset, followed by uranium. And then lastly, iodine, calcium, and serum anomaly they seem to be relatively robust. But if we expand to different kinds of fluids, we can see that this actually varies quite significantly, and namely that iodine calcium can change really dramatically, whereas uranium becomes more robust. So hopefully with this framework, we can start making predictions about how diagenesis actually affects these different records. Okay, so in combination, these models and data can help to develop a more mechanistic perspective of diagenesis. And with all this data, I think we can do a better job looking at the statistics to help us distinguish how to evaluate these proxy data in carbonate rocks. And so, for example, it becomes really clear looking at this iodine-calcium ratio that we shouldn't be using the mean values at any point, and perhaps the maximum value, although that still doesn't quite match the mean value we see in the modern ocean. But maybe some kind of corrective factor is needed. We can also couple these with water-rock interaction or diagenetic models to be able to predict why these proxy data will actually vary. And so we can couple, instead of just throwing out the bathwater, we can start to take a more critical look at how we would evaluate this data. Okay, so let's turn back to the first order trends that I pointed out at the beginning of my talk, where I posed the question, how much of this can be attributed to diagenesis versus an actual change in seawater oxygenation? And I think with the model framework, we can start to actually evaluate this a bit more carefully and critically. So for example, we learned that meteoric diagenesis would result in lower iodine-calcium ratio. So we could perhaps say that prior to the Precambrian, maybe all of these just happened to have some really severe meteoric diagenesis. But we also learned that under that scenario, uranium isotopes would not change, or if anything, have higher values, whereas we see the opposite, they're lower. And so I think with this combined framework, we can actually try to interpret these more carefully with the bulk of data that we now have. Okay, so I want to take a step back and connect back to sustainability. Again, to understand what might happen to the oceans on longer timescales, we really have to look at examples in the past. And so there's more effort in using these proxies and looking at changes in oxygenation deeper in time, understanding the mechanisms by which you can get periods of increased anoxia. But of course, making these future predictions requires understanding these past events, and therefore requires really useful quantitative tools. And so I think that means being able to look at diagenesis more carefully when applying and interpreting these Paleoredox proxies. And so I think a lot of the future research questions of the field in general is focusing on how diagenesis can be evaluated and assessed for in these records. And that's it. Thank you.